Okay. The last speaker, Ilias Kazantzidis, is a PhD student from University of Southampton. His research is on safe reinforcement learning, focusing on methods that use a human in the loop. So today's talk is about human in the loop safe reinforcement learning. Let's welcome Ilias to give the talk.
Hello, thank you for the invitation. So I guess you can see the slides, right?
Yes.
Great. Yeah, so I'm Ilias. I'm an integrated PhD student at the University of Southampton, and today I'm going to talk about safe reinforcement learning with a human in the loop. So I'm first going to give the motivation of my research, then present an overview of the different methods, and later I will present a work of ours that was published recently. So first about the motivation. We all know that reinforcement learning has achieved great things during all these years, but since it is a trial and error approach, it cannot be used directly in the real world. If it was used directly in the real world, it would mean that a machine, for example, that it would want to learn to drive, it would have to bump into different posts in order to explore and learn not to bump into them. So safe reinforcement learning tries to address this safe exploration problem. However, I have noticed that a lot of techniques, although they guarantee good performance and safety at the end of training, and they can apply it during deployment, they do not guarantee it during training. Moreover, if we try to transfer this knowledge from the simulations that these policies potentially trained to the real world, this will probably be quite brittle because of the well-known reality gap. So a way to do it is to try to do learning directly in the real world. And of course, there are many ways to do safe reinforcement learning, but one way, different ways such as constrained reinforcement learning, constrained MDBs, and all the other things that were discussed in previous talks. But one way that we are doing it, my research, is that we are using a human, because if the human is always there, we can obviously guarantee good performance and safety during the training. However, we come with a question. The question now becomes how much human burden, how much human time are we going to sacrifice for supervising and guaranteeing this safety? So it's all about this trade-off. Before I start discussing the literature, I would like also to talk about why traditional reinforcement learning really doesn't work in the real world. So one reason is the lack of a proper reward function. So in robotics, for example, we cannot even design a proper reward function about how to do different tasks, for example, about cooking. Another reason is that these rewards may be sparse or delayed. They might come after a lot of steps, and we will have to wait all the time. A third reason is sample inefficiency, which means that it might take, so for example, in Atari games, all these simulation applications, it was taking so much time, so many steps for the training to finish. If we were trying to do this in the real world, we would have to spend so much time, and we wouldn't be able to wait all the time. And of course, we have the safe exploration problem, which I discussed in the previous slide. And in that case, we can see the problem going from the safe reinforcement learning to safe reinforcement learning using a human in the loop. However, the literature also sees the problem in another way, which is we try to address this agent alignment problem. This means that the agent, although has a reward function that it is trying to optimize, when it optimizes it and finds a policy, this policy is not really consistent with what the human wants to do. So an example that maybe we will, some of you will have come up is the one of the boat which makes circles and receives coins instead of continuing to the boat race. which is known as the reward hacking problem. And in this case, we can see the problem was going from human in the loop reinforcement learning, studying all these methods that they're not necessarily concerned about safety, and going to human in the loop safe reinforcement learning. So start discussing about also safety critical applications. So I have put here some of the fundamental papers in different techniques, and I have tried to group them. Although this list is not totally complete, there are some fundamental papers and some state-of-the-art ones. So here we start with human in the loop, safe reinforcement learning. So I have put this in brackets because not all papers are concerned with safety. However, it is important to study all of them. And as a first separation, we can see that we have on the one hand learning from demonstrations, which is pretty much that we provide as humans the agent with many trajectories by executing a task, and we are expecting the agent to learn to either imitate us, which means constructs a function which maps the states to the human actions by supervised learning, or do inverse reinforcement learning, so learn first the reward function from our actions, and then apply this, and then use this reward function to do the traditional reinforcement learning. But on the other hand, we can have some other type of human feedback. So we here with human guidance, and we can separate them in these three categories. So in the first case, we have evaluative feedback. So this terminology maybe is not pretty standard, but I have seen it in previous surveys, and I continue with it. So in evaluative feedback, we will have one state action pair, so one state action pair or a full trajectory, and we will give some feedback to it. In human preference, we will have two of them, and we will compare them, either state action pair, so one state and one action, or a trajectory, a couple of states and actions in a row, or reward sketching that we will have just one trajectory. So in evaluative feedback, we have the simplest technique called policy shaping, which means that the agent will get a feedback about is your policy good or not, and we will either keep we'll get a feedback about one state action pair, and it will either remove that action if it's not good, or it will keep following it if it's good. So it's pretty simple, and I think it's not used anymore. But reward shaping is more of an advanced technique. Here there is a well-known technique called tamer, which means that either on the state action pair or on a trajectory, the agent will get a feedback in a value as a reward, and then it will be a reward model, reward function from all these rewards that it gets in different either state action pairs or trajectories, and we'll use this reward model to do traditional reinforcement learning at the end. So it will not use the initial environmental reward, but it will build a reward model. And here we have one paper which is considered about safety. So the papers that are considered specifically about safety, I have put an asterisk here. And I will describe this paper in a bit because it is extended also in this type of feedback in 3D environments. So continuing, we have the technique of human intervention, which we'll compare our method later. And this technique is precisely considered about safety, and it works in two stages. In the first stage, we can put a human here overseeing the agent, which learns by reinforcement learning, and it blocks an action if it is a catastrophic one. It replaces it with another action, which is safe, and it also gives a very negative reward. It penalizes the first action of the agent. In the meantime, it keeps a data set of all these state actions and the ground truth label, which was either safe or a catastrophe. So at some point, when it has seen a couple of examples, a couple of interactions, it stops and it builds a binary catastrophe classifier, which afterwards will take the position of the human. So after a while, there will be just a classifier which was trained by supervised learning, which will be deciding if the agent if the action that the agent throws, it is safe or not. Then there are more techniques like the policy-dependent feedback, which in that case, it's an interesting idea that the human's feedback is based not just on what they think is good, but also on the current policy of the agent. And then we can go to the most popular technique, that it is about human preferences. So this is more popular because it is considered to be more sample efficient, finished earlier. And let's see first the second branch here, which is learning a reward function. So learning a reward function is similar as to reward shaping, but instead of giving a value or a reward value, we give the preferences. So I prefer this action pair to this, or I prefer this trajectory from this one. And it was first introduced in this paper from Cristiano in 2017, where they were sampling segments from a trajectory. A human was saying, I prefer this one, the other one, or I prefer them equally. And then they were using something called a Bradbury-Terry model that it was optimizing a reward model in these preferences. With that reward model later, they could do traditional reinforcement learning as usual. It has also been used in conjunction with imitation learning. There are in this paper some interesting ideas about how to utilize also previous preferences. So this happens normally repeatedly in a loop, but you can also utilize off-policy data. You don't do it in an offline learning in this paper of Ilias and Abil. There are also some other interesting papers, even in text summarization or with interpretability or in multi-objective reinforcement learning. Finally, in reward sketching, there is this request framework, which is considered about safety specifically. And how this works is that we have initially some safe trajectories that we have collected them offline from human contractors. Then we can build a simulation of these trajectories, this learned dynamics model. And then we can sample from this dynamics model hypothetical behaviors, which are, for example, here we start with random imagined trajectories. This is the key idea here, that these trajectories are not really taken to the real world, but they are hypothetical behaviors. In these hypothetical behaviors, then we can apply the type of feedback the reward sketching one. So what is a reward sketch? Is this curve in which a human will be presented with a video sequence of frames, and when a frame is better than the previous one, then the curve will be going upwards. If it's worse one, based intuitively to what the human thinks, it will be going downwards. And this is a very sample efficient type of feedback, because the human can provide a lot of bits of information. So when the human provides these reward sketches, then we can build an initial reward model. And then based on this reward model, we can sample new trajectories, which are again hypothetical ones. This can be continued repeatedly until we have an improved reward model, which is pretty robust and good. And then what we have a reward model, we have the agent, we have also dynamics model, so we can do the pretty standard traditional reinforcement learning, and specifically model-based, since we have a simulation here. So now we can go and see the method that from a paper that we published recently. It's called JPAL HA, which is an acronym for Justified Human Preferences for Active Learning with Hypothetical Actions. And it uses sample efficient active learning technique of human preferences. So it's like what we discussed later about human preferences, nothing new, over two actions. So we are on state and we're comparing two actions. It builds on a previous algorithm called parenting, which was in the same branch, learning a policy directly. And as I said, in that branch, Yeah, I think I forgot to say that in human preferences, we can either build a reward model or we can learn a policy directly. So the difference in this case is that instead of building a reward model, we go and we optimize the policy directly. So here, we are in this branch here, learning a policy directly. And this is a paper that we built on. And building a policy, constructing the policy directly, optimizing it is potentially better about safety because we're trying to optimize the reward model, then we would potentially take unsafe actions. Moreover, we improve this model with two new ideas. The one idea is justifications, which means that we augment the preferences with a warning signal when at least one of the two actions from a state leads to a catastrophe. Human feedback becomes marginally more complex, but the impact on safety is significant, as we'll see later. And we'll describe more justifications. And hypothetical actions is that in the cases that we have a warning justification, a warning signal, then we want to explore more that actions by generating extra queries regarding those hypothetical actions that could have been taken hypothetically in the local area, because we want to investigate that area and potentially execute a better safe action. So let's see this in some more detail. We applied this in a simple environment because we tried first to see if our ideas worked. So here what happens is that the agent starts from the yellow cell, it tries to go to the red one, takes horizontal and vertical moves. It cannot go through walls, and if it goes to water, then it is a catastrophic failure. The agent, which is here a policy, which is a convolutional neural network, can observe this whole state, and the participant here, the person, the human, can also see the state of the board. And there is an interaction between the agent and the human. The agent asks preference queries and also justification queries. Preference queries are, I prefer the first one, I prefer the second one, or I prefer them equally. And justifications are warning if at least one of the two actions, as for example here, goes to water, or no warning if they are both safe. So for example, if it was up and right, then it will be no warning. In the algorithm, so the algorithm starts here. Let's quickly go through it. And we asked, so we will not always be asking questions to the human because we said we don't want to bother them always, but we will ask a query with this probability, which is a hyperparameter, which is close, should be close to 1, and the bigger it is, it implies more queries raised to the familiarity of the current state. The familiarity is the number that the number of queries that we have asked from that state. So if that you have never been to that state, then we should definitely ask a query from there. So if we go to the left here and ask a query, it means that we will sample two actions. We will receive the preference and the justification from the human. If the justification is no warning, then we can simply find which is the correct action, correctly chosen action for execution. And we can also map this preference and justification to the ground truth label, this MAU, which is in the list of these numbers, where 0 means I prefer the first action with a warning. 0.25 means I prefer the first action without a warning. They're both safe, but I prefer one of them. 0.5 means I prefer them equally because they are either both bad or they are equally both good. And 0.75 and 1, it's opposite to 0 and 0.25. So when we have MAU, the ground truth label, we can add this entry. So the state, the two actions, the ground truth label, and we also keep these in order not to repeat the same questions later. We add them to an embraced memory, to a data set essentially, that we are going to learn by with supervised learning. We also execute the action because essentially the human chose it. So we are finished from this branch. If there is a warning, then we will go to the hypothetical actions, the second idea. That I will not get into detail now what's happening, but the basic idea is that the agent, for example, here, it would start also asking about what if I go right, what if I go down, and it would map out this whole region immediately and potentially find a better action. So these all samples go in this data set X, and then it trains the policy pi, so the probability of picking one action from the current state with gradient descent, minimizing the binary cross entropy loss between the ground truth label, which is essentially how much do I prefer the first action to the second one, and the probability distributions that comes from our from the output of the CNN. If we were going from the right branch, essentially we would execute the greedy action, because here we would be in a case that it would be probably safe, since we didn't want to ask a question. So this would be probably, this would have been decreased. This number would go up. This whole thing would go down. So we would probably be in a safe case that we have visited. So we would execute the greedy action. And what happens here is that sometimes we also want to safely explore and ask some sort of unconventional questions. So we could record in a temporary memory R a pair of the greedy action and a random one, and ask these queries with another probability to the human at some later point. That's why these are called after the fact queries, ATFQ, instead of these ones, which are called BTFQ, before the fact queries, because they are called before the fact. So when we gather all these samples in the data set X, we do a training, and this happens until we find the optimal policy and the algorithm finishes. Let's see some results. So first we compare with traditional reinforcement learning algorithms, and specifically with Q-learning and SARSA, but they didn't make much difference. And we saw that these algorithms, as we can expect, they totally fail because they have no mechanisms about safety. So we can see that in this simple environment, we also tried different configurations, but the trends remain the same. We saw that it suffered more than 10 deaths, the blue one, and it was also quite late to finish, so it took 22.9 episodes to find the optimal policy. Instead of JPAL-HA, our algorithm, which sometimes had, so this was over, here we averaged over 1,000 trials, and only in the beginning sometimes it had one death, but in reality it was really little, and it found the optimal policy in only 3 episodes. We also compared with human intervention reinforcement learning, the method that I explained in the beginning, and we put a setting that also HRL would suffer almost no deaths, but we see that JPAL-HA was significantly better in terms of sample efficiency. So HRL would finish in 7.54 episodes, which is more than half than JPAL-HA. Then we also compared with parenting, and with JPAL, which is essentially, so parenting uses just preferences. JPAL uses preferences and the warnings, no warnings bits, the justifications ones. And JPAL-HA uses both these plus hypothetical actions. And we see consistently that for all different values of the hyperparameter, that JPAL is better than parenting and JPAL-HA is better than JPAL. Plus, we can also see this trade-off between safety and the human burden. So we can see that the bigger that this hyperparameter is, so the more questions that are asked to the human, the less will be the deaths. If we zoom in this square here, and we want to see what exactly happens, not only in terms of training deaths, but also in terms of time, we go here and we say what happens at 0.95, which is quite a conservative setting. So we see that the deaths are always pretty little, and we can see that JPAL, the training deaths decrease with JPAL, and then they decrease with JPAL-HA even more. However, the queries increase with JPAL, but we can drop them with JPAL-HA. However, there is a caveat that justifications are assumed to be a small additional cost. This caveat, we will take it out by considering that justification take a considerable amount of time compared to preferences. And we saw that with a real world experiment. So there were participants here that controlled the robot with, we made this interface here that they were asking about the preference or the alarm signal, the justification. And they also had the option to talk in a microphone if they wanted and use the method. So this robot was called Themion, and we're recording the time to see what actually happens in terms of time. There were participants from all different genders and disciplines, and they took some practice in the beginning. We randomized the conditions, so the configurations and also the order of the methods. And we saw here that the average time of justifications were indeed less than the average time of preferences, but it was still comparable. However, the average time for these three methods, we saw that parenting took, as we expected, less time, 3 minutes and 24 seconds. JPAL took 4 minutes and 2 seconds, but JPAL-HA had less time than JPAL, so 3 minutes and 51 seconds. So this relationship here holds. And with some significant tests that we did, we saw that there is not a significant difference in terms of time between parenting and JPAL-HA if we use a significance level of 0.01. So the p-value was 0.03. Also, if we consider one participant who took the minimum time, we saw that with the minimum time was 2 minutes and 47 seconds. And we can say that the training can be completed in quite a reasonable time for a real world task. Finally, regarding impact, we also tried this configuration in an outreach activity at the Southampton Science and Engineering Day, where we had 60 people trying this activity in 25 groups, 10 to 15 minutes each, and we had a couple of visitors actually in our room. The outreach activity was designed by my colleagues, Jennifer and Olaf, and by me. So in conclusion, we have this algorithm, JPAL-HA, that we were able to, with these two ideas, that we were able to decrease the training deaths and control the number of queries issued to the human and the overall steps, interactions. As future direction, we'll try to integrate these two ideas to safe reinforcement learning frameworks, such as the request that we discussed later, but they use reward modeling instead of learning directly the policy. And we are also trying to do it for more complicated safety critical robotic tasks using this Tiago robot that learns directly from raw pixels. So I think that's it. Thank you very much.
Thank you very much. Can you talk more about the future direction, especially for the complicated robotics tasks?
Mm-hmm.
So in your opinion, what is the suitable task to work on this field?
Yeah, so the question is about scalability, right? How do you think this method can scale to more complicated tasks?
Yes, and what is the suitable task for people to work on this field?
So we're thinking of making a task with this Tiago robot here of setting up in a desk some task like putting boxes one on top of the other. And it will learn, so it will be able also to generalize because it will learn from raw tasks. People will be able to teleoperate the robot or give the feedback in terms of human preference again, and also adding the ideas of justifications and hypothetical actions. Because in this example that we have, we were not considering learning from raw pixels. We were considering that we have the state of the board. which normally is not the case.
Okay, so in your opinion, this task could be a benchmark for safety robotics research.
Which task can be a benchmark for?
I mean, the task you just described, you think should be a suitable task to be a benchmark in this field, isn't it?
So this was from this paper. It was a simple benchmark, the island navigation environment, that the agent shouldn't go in the water. And there are a few more in OpenAI, which I don't remember all the names, but I think all papers do something different. They set up an environment or they on their own. So for example, this request paper has, so this one that I was describing, has a cliff edge environment, which says that when the agent goes at the edge of the board, the agent will cause a catastrophic failure. Or when it goes in specific squares within an arena, it again dies. So this is the problem, actually, that there are not so many benchmarks. OpenAI has some, but yeah, this is a very good question, actually.
Okay, thank you very much.
Okay, we have one question in the chat, but I think Yalidu is typing an answer. Is this correct, or should we answer this? She can answer live, I guess, or maybe the speaker can answer live if this is suitable. So I have one general question. What is the key difference between safety layer and human in the loop reinforcement learning?
I don't know what safety layer, I don't know what safety layer means. Sorry. Oh, a safety layer.
Maybe you had something in your presentation related to that, or if it's only human in the loop?
Maybe here. Yeah, so here I was describing all the methods that they had to do about human in the loop reinforcement learning, but I was pointing that some of these methods are considered specifically about safety. That's why I'm putting safe in a bracket here. And so these are all the methods that use a human in the loop. And I was putting an asterisk here to specifically methods that they are concerned with safety. I don't know if.
Okay, thank you. I think this answers also, you can type a more concrete answer in the chat. Now we have to continue with the next speaker. Thank you very much.